All right, so let's look at the questions that I assigned from section 1.7. So these first two, um, we want to find basically draw a bifurcation diagram um, for a differential equation that has a single parameter. Couple ways to go about this. Since I assigned two questions that are basically asking to do the same thing, I'll go about this a couple different ways. So for this one, just because it's easier for me to kind of understand what's going on, I'm going to rewrite this in descending order of powers. So y squared minus 2y plus lambda. Um, so I am being told, for my bifurcation diagram here, um, what values to use for lambda. So I'm just going to go ahead and apply that. So parameter generally goes on the horizontal axis. Dependent variable typically goes on the vertical axis. So -1, let's go a little wider. -1, -2, +1, +2. All right, let's just go from left to right. So when this equation looks like this, y squared minus 2y minus 2. So basically, essentially what a bifurcation diagram is, at least in part, it's not, in essence, it's not that different from drawing a phase line. Think of a phase line, metaphorically speaking, as a thread in like a rug. Basically, I'm going to stitch a few of these phase lines together, and that's what a bifurcation diagram becomes. Is me looking at a few different phase lines that describe how a differential equation or how its behavior changes as I alter this parameter lambda. All right, so y squared minus 2y minus 2. I don't believe this factors, so we can solve using the quadratic formula. Y equals -b, so 2 plus or minus the square root of b squared, 4, minus 4 times 1 times 2, 4 times -2, so plus 4 times 2, which is 8, all over 2. So I get 2 plus or minus the square root of 12 over 2. I can reduce radical 12 as, so radical 12, that's 2 times 2 times 3. So 2 plus or minus 2 radical 3 over 2. So finally, 1 plus or minus radical 3. So this tells me I have equilibrium points at those two places. So those are about where? So 1 plus radical 3, that's about it. Not quite 3. So let's draw our scale here. 1, 2, 3. So when lambda equals -2, I have an equilibrium point here. Actually, let's draw a phase line. So I have an equilibrium point here, which is 1 plus radical 3. Radical 3 is about 1.7, 1.73. So about 2.7. And then 1 minus radical 3 will be a little bit less than 0, not quite -1. So about there. Now to complete this phase line, I need to know what's happening, or what the value of dy dt is, or what the value of y prime is for values of y, like, between these points, greater than both points or less than both points. So I'll start with 0. When y is equal to 0, then y prime will be equal to -2, so I have a decrease. When y prime is equal to, let's say, Like I said, 1 plus radical 3 is about 2.7, so I'll just choose 3. 3 squared is 9 minus 2 times 3, which is 6. So 9 minus 6 minus 2. That comes out to positive 1. So this is an increase. And let's use negative 1 as a value for something less than both my equilibrium points. So negative 1 squared is 1 plus 2 essentially minus 2. So I get a positive. All right, so here's my first phase line. I got my 2 equilibrium points, and I know what the behavior looks like outside of those. All right, so moving on. So I'm going to go ahead and cross off negative 2 because I've done it. What happens with lambda equals negative 1? So y prime equals y squared minus 2y minus 1 equals 0. Does this factor? No. So quadratic formula again. So let me move this window. I don't need it. Y equals negative b. So 2 plus or minus the square root of b squared. 4 minus 4 times 1 times negative 1. So 4 plus 4 all over 2. Radical 8 reduces down to 2 radical 2. So now I get 1 plus or minus radical 2 over 2. All right. So again, I have 2 real roots. Radical 2 is about 1.4, so just a shade less than what we just had. So if I draw a phase line here, I'm going to have equilibrium points that kind of came a little bit closer. Still a little bit bigger than 2. 1 minus radical 2. Hey, hold on. Oh, it's not 1 plus radical. Okay, sorry. That makes more sense. 1 plus or minus radical 2. Okay, so 1 plus radical 2 is about 2.4. 1 minus radical 2 is about negative 0.4, so I have an equilibrium point about there. And same thing, I found my equilibrium points, but I also want to know what's happening everywhere else. So again, plug in 0. Oh, sorry, I'm looking at this one now. If I plug in 0, I get negative 1, so decrease. I'll plug in the same values as I just did. So if I plug in 3 for y, I get 9 minus 6 minus 1. That's a positive number. 2. And then I will plug in negative 1. So that gives me 1 plus 2 minus 1. That's a positive number. So similar phase line, but the equilibrium points came a little bit closer together. So I'm going to cross off negative 1. All right. Next differential equation. What happens when lambda equals 0? I get y squared minus 2y. This factors. So I can factor out a y. I get y times y minus 2. So that gives me y equals 0 and 2. So I have equilibrium points at 0 and 2. Okay, so what's going on elsewhere? So let's test a value between 0 and 2. 1's a good value. 1 squared minus 2 times 1, that's negative 1, so I got a decrease. Let's test the value 3 because that's bigger than both of these. 3 squared is 9 minus 6, that's positive. And then let's test negative 1 again. 1 plus 2 essentially is 3. So it's nice when they factor. All right. Step 4. Y squared minus 2y plus 1. I believe this one factors as well. So how does this factor? So if this equals 0, then this gives me the equation y minus 1 y minus 1 equals 0. So this gives me a double root, or like only one distinct root at y equals 1. So one of the things we were told is to find bifurcation values, and we have essentially stumbled upon one. So when lambda is equal to 1, we have found that y equals 1 represents the only equilibrium point. So, and that's why this is the bifurcation value of y, is because for any value of lambda less than 1, we got 2 equilibria. And for lambda equals 1, that behavior changed to 1 equilibrium point. So that's what bifurcation means, is that number of equilibria changes. For what value parameter does that behavior change? All right, so now we just have to test two different values. I'll choose 0. If I plug in 0 for y, I get 0 squared minus 0 plus 1. That's positive. So for values below the equilibrium point, I have an increase. What about for values above the equilibrium point? Let's try 2. 4 minus 4 plus 1. I have increase as well. So when lambda equals 1, my differential equation increases everywhere except for the place where I have equilibrium. All right, so typically at a bifurcation value, you have equilibrium, you have one equilibrium at that point. And I would expect to have no equilibrium beyond it. So let's see. If I let lambda equal positive 2, so y prime equals y squared minus 2y plus 2 equals 0. Don't think it factors, so we'll go quadratic formula. And just to, in anticipation of what's about to happen, when I'm drawing these bifurcation diagrams, these are all real valued. I'm real values of lambda, real values of y. So if I get imaginary values out of my imaginary roots for y, then we're done. We're done looking. So y equals negative b, 2 plus or minus the square root of b squared, 4 minus 4 times 1 times 2, or 2a. So this is going to give me 2 plus or minus the square root of negative 4 over 2. Okay, so I am not looking for any real roots. So what does that mean? Well, I still have a phase line, but there are no equilibrium to talk about on that phase line. So really I just have to choose one point. So I know the rate of change dy dt is never going to be equal to 0. So that means this is going to be everywhere increasing or everywhere decreasing. So let's just plug in a value. 0 is convenient. 0 squared minus 2 times 0 plus 2, that's positive. So increasing absolutely everywhere. One last thing I'll do on my bifurcation diagram here is to, connect these points with a curve. So basically this curve is kind of a boundary line that shows that basically on the outside of this curve, we have increases. On the inside of this curve, we have decreases. And that, qualitatively speaking, we can, if we were to extend this diagram to the left, that behavior would continue. These equilibrium points would continue to trend in that direction, and so would those boundaries. All right, so that's all for 3. Let's go ahead and move on to number 4. Like I said, there are multiple ways to handle these, so I'm going to go ahead and handle this one in kind of a different way. That one, I just kind of did this kind of did that one like by brute force. I just drew all these without looking for bifurcation values. Now I'm going to start by, let's look for bifurcation values. The way we look for bifurcation values is, let's look at where this is equal to 0. So I think we're going to have an equilibrium condition at y equals 0. Well, let's not get ahead of myself. So if I set this differential equation equal to 0, which is what gives me equilibrium, then I have, I'll just rewrite it, lambda minus 4y squared times y equals 0. So I have two factors that when multiplied together equal 0, which means I can I can set them equal to 0 independently and solve them. One of them is y equals 0. The other one is lambda minus 4y squared is equal to 0. So I think that y equals 0, that is an equilibrium condition we're going to have all the time. So no matter what, we're always going to have at least one equilibrium point. The other part of this equation, this lambda minus 4y squared, this is the one that depends on a parameter. So let's investigate that. So since this one is governed by a parameter, this is the one where bifurcation might happen. So I'm going to go ahead and flip all the signs and say this is 4y squared minus lambda equals 0, which is an equivalent equation to look at. And I'm going to use the discriminant to figure out basically my boundary lines. And I can use the discriminant here because even though the differential equation we started with is not quadratic, it's cubic, this component, this factor of it, is quadratic. So for the discriminant, a is always the coefficient of your squared term, so that's 4. B is always the coefficient of your linear term. There is none, so that's 0. And C is always basically any term that's independent of variables, so negative lambda. So b squared minus 4 times 4 times negative lambda equals 0. B squared plus. So I get 16 lambda equals 0. So this means I have a bifurcation value of lambda equals 0. Okay, so I think that's what we found. So for lambda equals 0, we should have bifurcation, which means that at lambda equals 0, let's see what we found. So, for the last bifurcation diagram we drew, we just went from left to right. Now let's start at the bifurcation value and make sure that the thing we found is actually what we think we found. All right, so again, horizontal axis goes for the parameter, vertical axis goes to the dependent variable. We're going to let lambda equal y, which means lambda equals 0, which means the differential equation we're looking at is y prime equals 0 minus 4y squared times y, or negative 4y cubed. And if that's equal to 0, then that means that y is equal to, then the only root we're going to possibly have is 0. So on my phase line that's going to coincide with the y-axis or the vertical axis, I have an equilibrium at the origin. So also we knew that y equals 0 was going to be an equilibrium. So we only have that one equilibrium point. So let's figure out what's happening everywhere else. So essentially, I just need to choose a negative value of y and a positive value of y. So if I cube a negative value, I get a negative value. But then when I multiply it by -4, it becomes positive. So positive. If I cube a positive number, I get something positive. But then when I multiply it by -4, I get something negative. So I believe my phase line for this value of the parameter looks like this. I have a sink at y equals 0. All right. So now let's look immediately left and immediately right to see if we were right about bifurcation at lambda equals 0. So if lambda equals -1, what do we get? We get y prime equals -1 minus 4y squared times y, set that equal to 0. So for all of these, y equals 0 is going to be in equilibrium. That is going to be inescapable. So equilibrium here. The other factor I can set equal to 0 and see how that behaves. So -1 minus 4y squared equals 0. 4y squared equals, I don't want to use too much room. 4y squared equals -1. Y squared equals -1/4. That's not going to give me any real solutions. That's going to give me the square root of -1/4, which is not going to be real. So again, I'm looking, I have no other solutions to look at there. So I don't know if I found bifurcation because I don't see any change going back that direction. So I better see change going to the right. And here's the things. I'll check just this once, but it really should be the case that if I test some y value, so if I test a negative y value, so let's test -1. So this will be -1 minus 4 times 1, essentially. I'm doing a lot of assuming. Let's take this slower. Okay, so what if I plug in -1 to my differential equation? Let me go ahead and distribute. -y minus 4y cubed, which is the same as -y plus 4y cubed. So if I plug in -1 for this, what do I get? -1 minus 4, so that's -5. But if I, with the negative out front, I should have positive. And I think the opposite should be true if I plug in positive numbers. If y is 1, 1 plus 4 is 5, but I factored out a negative, so I should have this value here. I should have a decrease as well. So identical phase line. So let's make sure we have bifurcation if we go to the right. What happens when lambda equals 1? Then I get y prime equals 1 minus 4y squared times y equals 0. So, like I've already said a couple of times, that's not even close to good. Like I've already said a couple of times, we're going to have equilibrium at the horizontal axis, y equals 0. What happens if I set the other part of this equal to 0? I get 1 minus 4y squared equals 0, which gives me 4y squared equals 1. Y squared equals 1/4. Or y equals plus or minus 1/2. I get 2 real equilibria. So let's give ourselves some scales now. 1, -1, which means I have equilibria where? I have an equilibrium point here, an equilibrium point here, and hopefully now you're convinced that the bifurcation value we found is okay. Because basically anytime you have a positive value for lambda, you're going to have 4y squared equals that lambda. And as long as that lambda is positive, you'll be able to find 2 positive real roots for it. Okay, so now, if you believe everything I've been saying about like what these curves represent, then what I should have is this. I should have decrease, increase. But what's left up, like what we don't know is what happens at these, like in these other 2 little subintervals that we haven't had to worry about before. So we need to choose this point between 0 and 1/2. Let's choose 1/4. So if I put in 1/4 for y, I get 1 minus 4 times 1/16 times 1/4. So 1 minus a fourth, that's 3/4, times a fourth, that's 3/16, so that's positive. So a slightly positive value gives me a positive increase. What about when I plug in a slightly negative value? I don't think it matters. But let's make sure. Actually, I lied to you. I do think it matters. Because 1 minus 4 times, what's negative 1/4 squared? Still positive 1/16. But then I'm multiplying that on the outside by negative 1/4. So that's going to be a negative. Okay. So now I have phase lines drawn for -2, -1. No, I don't. I didn't do it like that. -1, 0, and 1. Here's the good news. I can draw the phase line for -2 right away because I know that since I found my bifurcation point and I'm understanding how this differential equation works, when lambda is negative, I can't possibly get any other equilibrium points except for that y equals 0. And also I know that the behavior elsewhere is going to be, it's going to follow suit from what I said it was at lambda equals -1. So I think I'm going to be done with -2. For lambda equals 2, I know I'm going to have similar behavior, but I should probably go through the work of figuring out where those roots are, or where the equilibrium solutions are. So y prime equals 2 minus 4y squared times y equals 0. Again, y equals 0 is, that steady equilibrium point. Equilibrium. But then I have to solve the other component. 2 equals 4y squared. Y squared equals 2 over 4, or 1/2. And I get y equals plus or minus 1 over radical 2. So those are a little bit further away. So about 0.7 and -0.7. But I can be confident that all of this behavior on the same side of this boundary curve that I'm about to draw holds suit. This is what's called a pitchfork bifurcation. I wish I could use other colors here, but basically part of my bifurcation curve is going to just coincide with the horizontal axis because I always have y equals 0 as an equilibrium point. The other part of my bifurcation curve is going to look like this rightward opening parabola, which kind of separates these increases from these decreases. So those are good bifurcation diagrams, and hopefully looking at those, seeing those two different ways that I approached it were valuable. Right, moving on. Sketch the graph of a function f of y, such that the one parameter family of differential equations d of y equals f of y plus lambda satisfies the below properties. So for all alpha less than or equal to -3, I have 2 equilibria. For all alpha greater than or equal to 3, I have no equilibria. And for alpha equal to 0, I have exactly 4 equilibria. Okay, so let's think about how to get this done. All right, so this question, there's many, many ways to go about this. So I'm going to show you one way that will fulfill these criteria, but that doesn't mean that, and you might have something that looks totally different and satisfies it as well. But I'll try to explain kind of what the key features of it are. So if we look at the way that, we're given a structure here. So dy dt equals f of y plus alpha. So what does our parameter do? Like, for example, if we look at some of our other equations I gave you, like this parameter lambda, altering it essentially, I'm adding lambda, which means I'm shifting the rest of my function up and down, or shifting the entire function up and down. In this case, lambda is doing something totally different, because I'm essentially multiplying lambda by y and subtracting 4y squared from it. In this case, what alpha is doing is this vertical shift. So let's say that f of y is y squared. Then what alpha is doing is essentially, if it's y squared plus 1, I just lifted everything up by a unit. Y squared minus 1, I just moved it down by a unit. So that's kind of good news and bad news, is that alpha is so limited in the modifications that it can make. All it can do is take whatever curve you're about to draw and just slide it upwards and downwards. So basically, whatever function you graph, it has to be something that vertically sliding it up and down, vertically translating it, can meet all three of these conditions. So here's what I'm going to focus on. I'm going from 2 equilibria to no equilibria to 4. The fact that I can have, as far as I know, a maximum of 4 equilibria, that makes me feel like, if I want to set this up as a polynomial, then this will be a 4th degree polynomial, or a quartic. I mean, so what do polynomials look like? What do they, if that's what they look like, then what does that mean? So let's kind of build up. A quadratic polynomial. So let's draw some quick pictures here. What do quadratics look like? Like, generally speaking, they kind of look like this. Let me draw one that doesn't double back on itself. So this is a 2nd degree polynomial. They can cross the x-axis twice. At most, they don't have to cross it twice, but they can. So this is 2nd degree. What about a 3rd degree polynomial, a cubic? They can cross the x-axis 3 times. And this is a theorem about polynomials, is that an nth degree polynomial has n roots. They aren't necessarily all real, but it has n roots. Just like you probably talked about this with parabolas. I think we probably just talked about it in one of the last questions, but a quadratic always has 2 roots. Sometimes they're the same. Sometimes they are both imaginary, but it always has 2 roots. Because I'm dealing with a situation where alpha, or where f of y can have 4 equilibria, I'm going to deal with something that is a 4th degree polynomial. That's what I'm going to try to work with. So let's play around with that. So when alpha equals 0, basically what I have is this. Let me be a little more specific. Alpha equals 0, that means that dy dt, that just equals f of y, right? Basically, whatever curve I come up with, whatever graph I come up with, that's going to be this unaltered. So let me try to draw something that crosses the x-axis 4 times. Let's give it a shot. So 1, 2, 3, 4. So this is alpha equals 0. Does this thing have 4 equilibria? Okay, I think it does. So there's one, there's one, there's one, there's one. So I've definitely satisfied part 3. Okay, what if, so let's look at one of the other 2 bullets. For all alpha greater than or equal to 3, the equation has no equilibria. So basically, if I make alpha a positive number, and to be clear, what is this going to look like if I make alpha a positive number? So alpha equals 3 means that dy dt equals f of y plus 3. That is going to make my graph do what? Well, it's going to slide it up. So it's going to make me lose some equilibria, but not all of them, because this graph continues downward infinitely. So at most, I'm going to lose 2 equilibria. I might have a graph that looks like this. Okay, so I need to reconsider because I don't think this is going to get the job done. But here's what I can do instead. What if I take the graph that I just thought about and mirror it? So instead of a graph that continues infinitely downward, what if it's a graph that goes infinitely upward and crosses at all those points? So 1, 2, 3, 4 equilibrium continues infinitely upward. Now let's think about this. What does this curve look like if I add 3 to all my f of y values? Well, now it should look something like this, roughly speaking. So now, since this curve extends infinitely upward but not infinitely downward, I should be able to add alpha, a positive alpha to it, and remove all my equilibrium points. So I feel good about item 2 and item 3. Let's make sure that when alpha equals -3, which gives me dy dt equals f of y minus 3. What happens if I take the first graph I drew and reduce it by 3? I want to have exactly how many equilibria? I want to have exactly 2, right? So I want to reduce it so it looks like this. So I have an equilibrium point here, an equilibrium point here. And what it says is for all a less than or equal to -3. Since this graph continues infinitely upward, it doesn't matter how low I make this graph, it's still going to cross the horizontal axis twice. Let's make sure I believe that for a greater than or equal to 3. Yeah, no matter how high I shift this graph upward, it's never going to cross the x-axis or the horizontal axis. And then the other one for alpha equal to 0, that's a single point, and I already verified it there. So again, this is one way to make this happen. There are there are certainly other ways you could make this happen. I'll give you specific feedback on yours. All right, final question. All right, so I have a population model given by this differential equation. So this is how a population of deer, looks like there's a birth rate in here given by 2p, a death rate given by p squared over 50. We're also going to alter this equation by, allowing hunting licenses. So how does that alter this equation? So the number of hunting licenses, it's going to be unknown for now, not variable, but unknown. So that's a parameter. So that will alter our equation. So dp dt equals 2p minus p squared over 50 minus 3h, because I want h to stand for the number of licenses I'm going to give out. And on average, each licensed hunter will kill 3 deer. All right, so this is our new equation we're going to deal with. A, what is the largest number of licenses that can be issued for the deer population to survive? So essentially what this is asking for is a bifurcation point. So we can treat this as a quadratic. We have a squared p term, a linear p term. That's a quadratic. So let's identify A, B, and C. A is equal to -1/50. B is equal to 2. C is equal to -3h. I'm going to set up a discriminant and set it equal to 0 because that's kind of like the boundary line. When do I go from having 2 real roots to 1 repeated root to 0 real roots? So b squared, 2 squared minus 4 times A times C equals 0. So 4 minus 12h/50 equals 0. 12h/50 equals 4. 12h equals 200. H equals, I don't think that's divisible by 12. 200 divided by 12 is 16 2/3. So for now, we'll keep that number unrounded. All right, so this is the largest number of licenses that we can issue. So what happens to the deer population if this many licenses are issued? Okay, so now let's alter our differential equation. So if h is equal to 50/3, then our differential equation becomes this: dp dt equals 2p minus p squared over 50 minus 3 times 50/3, which is 50. All right, so let's figure out. So this is an autonomous equation. Let's see if I can model it with a phase line. Set it equal to 0. I'm going to try to clear the fractions by multiplying everything by 50. So what does this give me? This gives me 100p minus p squared minus 2500 equals 0. So p squared minus 100p plus 2500 equals 0. And I get p, this factor is the perfect square actually, p minus 50 squared equals 0. So p equals 50. So I essentially have found an equilibrium population for my deer, and it's the only equilibrium population there is. So 50 deer is an equilibrium population. What happens if I have more or less? So we rewrote this equation to p minus 50 squared. Since I'm squaring this, if it's not 0, it'll be positive. So I'm going to have a node at 50, basically. If I have a deer population below 50, it'll increase to 50 and stabilize. If I have a deer population above 50, it'll increase. All right, so that's what's going to happen if we issue those 16 2/3 licenses on average every year. So that's what's shown by that phase line. Draw a bifurcation diagram for the parameter, which represents the number of issued hunting licenses. All right, so let's draw this bifurcation diagram. Let's just do 3 phase lines. We'll do one for the equilibrium condition, and then one on either side. Okay, so we said that our bifurcation value of H is going to be 50 over 3. Let's choose a couple of values for H that are, reasonably far away from that. Let's say that H will do 25, and we'll say H will do 10. So this is about 16 and 2/3. Yeah, 10's fine. I can just drop in my phase line from what I just drew for part B. So at 50, I have equilibrium and I have a node where I have an increase on either side. Now, to figure out what's going on above and below that parameter value, let's go below first. So dp dt equals 2p minus p squared over 50 minus 3 times 10, which is 30. All right, so when I let h equal 10, I want to solve this equation right here. Set it equal to 0 and solve to figure out what my new equilibrium conditions are. So again, I'm going to multiply by 50 just to avoid dealing with fractions. So 100p minus p squared minus 1500 equals 0. P squared minus 100p plus 1500 equals 0. No chance that factors, does it? Let's see. Oh my God, we got lucky. It does factor. No, it doesn't. Oh yeah, I was wrong. Okay. All right, so let's do quadratic formula on this. So P equals 100 plus or minus the square root of B squared. So 1, 0, 0, 0, 0 minus 4 times 1500, so 6,000 all over 2. So I get 100 plus or minus the square root of 4,000. What is the square root of 4,000? 63.25 all over 2. So my two values are 81.6 and 18.4. Okay. So my phase line for this situation, I have equilibrium points at 18.4 and 81.6. And I have a good idea of what's going on outside that boundary. I have increases. And I suspect that I have a decrease inside that boundary, but let's find out. We can go ahead and plug in 50 because it's inside that boundary. So 100 times 50, 5,000 minus 50 squared is 2,500. So essentially 5,000 minus 4,000. Oh, that is not what I thought. Am I right? Let's see. 50 squared. Let's make sure. 50 times 50, 2,500 minus 100 times 50. Oh, that's going to be okay. No, it is a decrease, about negative 1,000. Okay, so we're going to decrease. And then what happens to the right? So if we choose 25, this should be very quick. So what's going to happen is dp dt equals 2p minus p squared over 50 minus 3 times 25, which is 75. If I set that equal to 0, let's just go straight to the discriminant. B squared, 4 minus 4. So 4 is b squared. B squared minus 4 times a. Now let me start over. B squared minus 4 times, left off the negative, times a times c. So what does this come out to be? I think it's going to be 4 minus a large positive number. So 75 over 50 is 1.5 times 4. So it's going to be 4 minus 6. So the discriminant is negative, which means that I have no equilibria. So my phase line is going to have one behavior. So I just got to pick one value, plug it in here. I suspect that if I'm giving out too many hunting licenses, my population is going to die off. So I would expect to see a decrease. But let's make sure. Again, it doesn't matter what I plug in. So let's just plug in. We've been plugging in 50. 0 doesn't really make sense to plug in. So 2 times P. So 100 minus 2,500 over 50 minus 75. I get negative 25, so I do get a decrease. So the population will die off with this many hunting licenses. So one thing I want to make sure of, I want to go back to my equilibrium condition. So we said that H was 50 over 3. That was our equilibrium condition, which when we do that, we get 50 for our constant term here. So 2p minus p squared over 50 minus 50. Multiply through by 50, we got 100p minus p squared minus 2,500. I flipped all the signs. P squared minus 100p plus 2,500. Does that really factor to p minus 50 squared? P squared minus, yep, I think so. Okay, let me make sure about something. If I plug in 100 for p, I get 200. I just don't like the way my bifurcation diagram looks, and I'm gonna check it. 200 minus 100 times 100 over 50 minus 50. Okay. No, I got a decrease here. I'm glad that I checked this. Okay, let me check a value below. Let's just try p equals 10. 20 minus 100 over 50, which is 2 minus 50. Okay. Now I feel like I got to check everything. So in the case where I have 2 equilibria, I suspect that all 3 of these are flipped. So when h equals 10, do I still have any of that stuff written down? Yeah, I do up here. So 2p minus p squared over 50 minus 30. I found my 2 equilibrium conditions at 81.6 and 18.4. So I plugged in 100 for p. Let me do it again. So that's 200 minus basically 10,000 over 50. Yep. I had all these flips, so I'm going to go ahead and just erase everything and double check. If I plug in 50 here, I get 100 minus 50 minus 30. That's positive. And then I suspect this last one will be a decrease, but let's be absolutely sure. If I plug in P equals 10. So 2 times 10 is 20 minus 100 over 50. So 20 minus 2 minus 30. That's a negative number. Okay. At last, I feel good about this bifurcation diagram. So only in the case where I have two equilibrium points, when I have populations in between those equilibria, is my population going to be increasing. Otherwise, the deer population is going to be, at risk of dying off, or at least at a very unstable equilibrium. All right, that is all for this section.